All right, let's learn some more inference. Inference about a population mean. During this lesson, we're going to do these things. Really, we can kind of breeze through this, okay? Super important. We're going to be using a T distribution. So, you were actually going about it. You're actually finding a Z value, right, with a proportion. And you notice also that if you're going to do a confidence interval about a proportion, instead of using your critical value that you're going to use is going to be a Z star critical value, right? And then when you're doing a confidence interval about a mean, you are doing a T star. And so the same thing is going to be true. We're going to use a T distribution, except for if the population standard deviation is known. But really, if the population standard deviation is known, then there's a darn good chance you actually know the population. As a matter of fact, it's probably if you use the mean to calculate the standard deviation. So, all right. Let's test the plane. So, a company claimed to have developed a new AAA battery that lasts longer than its regular AAA batteries. Based on years of experience, the company knows that its regular AAA batteries last for 30 hours of continuous use on average. A simple random sample it throws me off when I say a simple random sample and then it says and I'm like, but it's all correct. So we got SRS of 15 batteries. They lasted on average 33.9 hours with a standard deviation of 9.8 hours. Seems like a fairly big standard deviation. So we have convincing evidence that the new batteries last longer on average. So we would find a significance test where our null hypothesis would be that the mean is actually 30 hours. And we're suspicious, right, that the mean battery life is actually larger based on the sample that we found. Or that we so then our alternative hypothesis is going to be that perhaps the population mean is actually greater than 30 hours. All right. So that's what the notation is going to look like. So our parameter of interest is going to be mu.
Once it starts, it doesn't stop.
Can you stop over there?
Once it starts, it doesn't stop.
So remember, we had conditions that need to be met for population mean. They are the same for a significance test as they are for creating a confidence. And it's pretty much, yeah, I'm sure you guys are all used to this. Remember, for that, right, if the sample is 30 or greater, just go ahead and say, hey, we can assume the data is normal. If it's not, then what we're going to have to do is look at what the distribution of the data, if you have it, and then use a graph to actually tell whoever's reading your inference that you believe that it's approximately normally distributed based on the shape. And the fact that there are no outliers. But that's not something new. All right, we're going to carry this thing out. We're going to have our test statistic. So now we're going to use a T test statistic. It's going to get a little different. We did find critical values based on degrees of freedom, right? And now we're going to actually find a probability. based on that. So our test statistics is always right. Statistic minus parameter divided by standard deviation. We know that the standard deviation is going to be a sample mean, and that sample mean, the standard deviation of the sample mean, is going to be our standard deviation divided by the square root of our sample size. So we won't be able to use this, is what you're saying, right? We're not going to know this, right? It'd be unusual for us to know that. So instead, we would use the standard deviation of the sample, and that will be O. As long as we can assume that the data is normally distributed, it's going to be okay for us to use the standard deviation of the sample. All right. So if we were to carry this thing out, this is what it would look like. We've been given X bar, we've been given the standard deviation of the sample. Make the calculation, you get 1.54. And then from that test statistic, we'll calculate a p-value. So let's look at our t-distribution tables and look at how we find that p-value. All right, so if we get a test statistic of 1.54, we'll go to our table, and there's a little illustration of it here, right? But let's look at the bigger picture of it. So we know that we had a simple random sample of 15, so we'll go to 14 degrees of freedom on this. And Jordan, I need to remember what that was. It was 1.54. 14 degrees of freedom. I think it's just nicer to look at the whole table. So we'll look at 14 degrees of freedom, and we'll look for 1.54. That is somewhere in here. So what that means is that we have a probability of between 0.5, 0.05, and 0.10, right? So it's certainly greater than 0.05. Now, if we do this on our calculator, we'll get a much better answer.
For our house.
So I can go ahead and hit menu. So we will choose statistics, stat tests, and now we're going to go with a t-test. T-test.
Two samples? Oh, wait, that's...
Test the t.
Whoa.
We are not going to use data. Come on. I said we're not going to use data. We're going to use stats. We would use data if we just had a list of numbers, right? And we had to calculate the mean and all that stuff, okay?
Wait, how do I...
I mean, in this case, we're given some statistics. Hit enter. All right, so our hypothesized mean was 30. The mean of our sample was 33.9. Standard deviation was 9.8. Oh, brother.
Gravity.
And we had a sample size of 15. Our hypothesis is that the population mean is actually greater than our hypothesized mean. Than our...
did I do that?
And so we get a much more precise p-value, right? From our table, all we can say is the probabilities between 0.05 and 0.1, right? But here we're able to get an exact p-value of 0.07. It's pretty good. It's much better, I think. I feel like it's so weird to say that the probability is between this and this. But I mean, then again, if you know that it's greater than 0.05, then you know that you're going to go ahead and reject the null hypothesis, right? So you can get enough information just using the table to know whether you're going to reject or fail to reject the null hypothesis. But I just feel like it's much nicer to have a real number, right? So I prefer to do it like that. All right. It's talking about using the table B and what you're doing with the range. And honestly, I feel like unless your calculator broke, or like you ran into something, you should just use your calculator to do this. You really should. But as a backup, you can use table B. If you're like, if you forget how to use your calculator and somehow remember table B, I mean, go for it. But it does not give you as good, it doesn't give you as reliable of a number. It's not as good, it's not as accurate. So, yeah. But it can be done. So here we go, new test, one sample t-test. We got a test statistic. Again, when you're actually performing inference, if you're going to use your calculator, you'll fill in the values, right? You'll substitute in the values for x bar, mu sub naught, s of x, and n. Get that test statistic, but you'll get you'll use your calculator to get a p-value. And then even to get that test statistic, right? Because you notice that on that calculator page that I showed you, it gave you a t value as well. Additionally, our rejection regions are exactly the same for our alternative hypotheses. Okay? There is a connection, obviously. The connection is about the same as it was for a confidence interval for a proportion and a z-test. Okay? Same connection. So oftentimes we'll have paired data, right? We'll compare stuff. You know, like for instance, you'll do an experiment. You'll have a control group, and you will have an experiment group, and you would like to know if there was a significant difference between two results. So what you can do is actually, rather than doing a two-sample t-test, you could actually subtract one mean from each data value from each data value. Subtract, right? And see if there's a significant difference. If there's not, then you would hypothesize the difference would be 0, right? If there is, you would hypothesize that it's greater than 0 or that it's less than 0. Or sorry, that would be your alternative hypothesis. So here's an example. They're wanting to find the effects of caffeine withdrawal. So they got 11 volunteers. You can read. You have to pay me a lot to be a part of this. I feel like I need some money. Funds. Before they make me quit caffeine. So they have a control group that takes a placebo, and they have a an experiment. So then they test them for depression. All right. So they measure their levels of depression. I'm not sure how you measure that, but it looks like it's on some sort of a scale. And then what they're doing is subtracting, just like I said, right? You're going to take one, subtract the other, and then you're going to find the mean difference. If that mean difference is not 0, right, we're going to say that there definitely is a difference. I think that they're trying to see if people are more depressed when they take caffeine. R-squared show more symptoms of depression. So the people that were having caffeine withdrawals, it turns out, are getting depressed. What? That's weird that we're going back to our experimental design unit for a moment and just kind of reminding you why we have to have some sort of random assignment. Just talking about the way they designed this experiment. I don't feel the need to read it to you. It seems to make sense. I might have left this slide out. All right, so now we're to the meat and potatoes of this. And just as I was saying, right, what you're going to do, if you're going to be testing if caffeine deprivation has no effect on depression, then you would expect that the mean difference in those scores is 0. And then if you think that it does cause depression, right, then your alternative hypothesis is that mean difference is greater than 0, right, if you're taking placebo minus caffeine. And I love how they're saying this now. No significance level is given. Use an alpha level of 0.05. We're going to run through this thing. I feel like what they did when they stated the parameter of interest, the mean difference of levels of depression, placebo minus caffeine, is your parameter of interest, and then go ahead and state your hypotheses, which has already been done. We'll go ahead and check the conditions. We aren't sampling. Okay. I feel like we have taken a sample.
They were volunteers.
They were volunteers? They recruited 11 volunteers?
That sounds like
Yeah, I guess we're not sampling from a population. That is interesting. I'm thinking my thought process is if you check the 10% condition, would you get in trouble for that? I don't think you would. have to be a mean grader. Um, because there is a sample being taken. That's interesting. All right, so we'll look at the data. Either of those graphs work. I've always said that the box plot is I think the most efficient way to make a graph of the distribution of the data. It has an irregular shape with SOV value. Let's see, the box plot shows some right skewness. I don't know outliers. You can look at a normal probability plot. I guess it would be safe to assume that you can use a T distribution. I don't want you to use this drawing. There's no point in getting your calculator will spit out everything that you need in order to find that p-value. As a matter of fact, so this is actually done on an 84. And we have the inspires, and they'll calculate a p-value for us. So that's the way we'll do that. We'll calculate a p-value. But the main point of this is we can wind up with a very low p-value. So we would reject the null hypothesis that the mean difference is 0. And we have convincing evidence that depression score is So we talked last time about how to increase the power of a test. You can increase your sample size, or you can decrease your alpha level, right? And that's pretty much what this is talking about. What this slide is referring to. So be aware that the larger the sample, the better, right? You might be able to find not much of a difference in a small sample, but if you increase the sample size, you would actually get it different. And that is all. We did some examples next class. We'll just do a bunch of inference. It'll be awesome.